everyone. I hope you guys are doing great. So this is in continuation to the blog post which is recently posted on our website. It's about electric circuits. So let's start with the most by defining what is a circuit. So a very simple circuit is something which I'm going to draw over here. So it has a simple switch which is represented usually customarily by S. It has an element which is a bulb, so this is how bulb is represented, and this circuit is closed along with the battery, so this is how the battery is represented, and it has a voltage of V. So this is plus and this is minus. So this complete assembly is known to be a circuit because this is a closed path. So whenever the switch S is closed, it enables the current to flow in this particular circuit. And current always flows from the positive voltage side. It starts from the positive side and it terminates on the negative side. So this is how the current flows. So that's why I've shown the current to be in this particular direction, and over here it is coming down. So this is how a simple circuit looks like, and this is what current, voltage, switch, and a simple element is. This element is usually termed as a resistance because it is offering some resistance in the flow of this current. Now this resistance can be a resistor, a capacitor, an inductor, or maybe a combination of any combination of these three. So that's what is the resistance. Let's move on to the representation about the series and the parallel circuits. So first, let's talk about how a resistor is represented. So if we talk about any resistor, and it is represented by something like this. This is the format in which we represent the resistor, or the symbol in which we represent the resistor, and the SI unit of the resistor is given by ohm, 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 and it is represented by this particular symbol. So this is how the ohm is represented. If we talk about capacitor, then the capacitor is represented by two parallel plates. So this is how a parallel capacitor, to be more precise, looks like. A parallel capacitor, this is the symbol. And if we talk about its SI unit, then the SI unit of the capacitor is given by farad, and it is represented as F. So this is how the capacitor is represented. Then let's talk about the series and the parallel connections of these equipment. So let's talk about first the resistors. And resistors, let's talk about their series connection. So whenever we talk about series means one after the other. So one after the other means the resistance are connected somewhat in this fashion. So let me take a different color here. So resistance are connected like this is the first resistance. After this we have another one. After this we have another one. After this we have another one, and so on and so forth. This is how the circuit continues, and these resistances would be said to be in series. If their individual values are R1, R2, R3, R4, and so on, then the equivalent resistance, which is represented by Req, where Req is the equivalent resistance, is given by the sum of the individual resistances. So that's going to be equal to R1 plus R2 plus R3 plus R4, and so on. If we add up these, then that would be the resistance which can be replaced, which can replace all these resistances combined, and that's why it is called an equivalent resistance. Likewise, we have a parallel connection of the resistors as well, in which each end of a resistor is connected by a same wire, and the other end is also connected by a same wire which has a negligible resistance. For example, these are a couple of resistances. So we take one end of each, which is the left one, and we take the left one only, not the right or left in the combination. We take the left end of each resistance. We connect them with a resistance-free wire, and we take the right side of each of the element of each of the resistance, and we connect them by again a resistance-free wire. And this connection now would be called a parallel connection because all of these are in a parallel. It looks like a ladder. All of these connections are in parallel. So let's call individual resistances as R1, R2, R3, R4, and so on. Then in this case, the equivalent resistance with which all these resistance can be replaced is given by 1 over R equivalent, that is the reciprocal of the equivalent resistance, is sum of the reciprocal of all the individual resistance. So that's going to be 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus so on. So this is how the resistance looks like. The equivalent resistance looks like. So let's consider some examples on finding the equivalent resistances, and which will make it a bit more clear. So let's say we have these two resistances between A and B. Let's say this is 2 ohm and this is, let's say this is 5 ohm. So what is the equivalent resistance between A and B? So we realize that these two resistances are in series, so the equivalent resistance is going to be the sum of the individual resistance. So that's going to be 2 plus 2 plus 5, which is 7 ohms. Let's talk about another question. We are given a circuit like this is the one resistance, this is another resistance, and over here we have the third resistance. This is point A, or let's say this is point A and this is point B. So what is the equivalent resistance between A and B? This is again, although it looks, it is as it is branched a bit downwards and then it again goes over here, but this doesn't change any configuration. It is again uh, a series combination. So if this is 1 ohm, this is 2 ohm, and this is 4 ohms, then the equivalent resistance is going to be 1 plus 2 plus 4, which is nothing but 7 ohms. This is how the equivalent resistance looks like. Let's talk about another question here. So we can have the resistances in parallel as well. So this is how the resistances looks like. We have these three resistances which are connected in this fashion, and they are across A and B. So we have to, this is 3 ohm, this is 6 ohm, this is 2 ohms. So we need to find the equivalent resistance, and in the previous case, what this means is equivalent resistances. We can replace these two resistors by a single resistor of value 7 ohm in this case. So this is one and the same. Likewise, over in the example 2 as well, between A and B, we can replace all the three resistances by just one resistance, which is of the value 7 ohm once again. Uh, Now A and B, we notice that all the three resistors are in parallel. So 1 over R equivalent is going to be 1 over 3 plus 1 over 6 plus 1 over 2. So let's add 1 over 6, 1 over 3, and 1 over 6. So their common LCM is 6. That's going to be 2 plus 1 over here plus 1 over 2. 2 plus 1 is 3, 3 over 6 is 1 over 2. So we have 1 over 2 plus 1 over 2, which is just 1. But mind it, this is 1 over R equivalent. So if we take the reciprocal of both sides, then the R equivalent comes out as 1 over 1, which is just 1 ohm. So what does this mean? This means that between A and B, we can replace all these three resistances by a single resistance of value 1 ohm, and it will not change. And this is how the equivalent resistance will behave. The connection can be a combination of series and parallel as well. And how's that? It can be something like this. This is the point A, this is the point B. This is, let's call it 2 ohm, this is 4 ohm, and this is 3 ohm. So we need to find the equivalent resistance between A and B. So first we have to find the equivalent resistance of these two connections because they are in series. So if we talk about the above one that could be replaced by a single resistor which has a value of 2 plus 4 because they are in series, so that can be replaced by 6 ohm, and this is already 3 ohm, and now these two connections are in parallel. So 1 over R equivalent is going to be 1 over 6 plus 1 over 3. That's going to be equal to over 6. We have 1 plus 2. So it's nothing but 3 over 6, which is 1 over 2. But mind it, 1 over 2 is not the answer. This is 1 over R equivalent, which means that if we take the reciprocal of both sides, R equivalent comes out as 2 ohms. It means that between A and B, we can replace that complete arrangement by a single resistance of the value 2 ohms. Let's talk about another example over here. So we have another hybrid combination of series as well as parallel. So this is how it looks like, and along this we have another resistor. So we have to find the equivalent resistance between A and B. This is 1 ohm, this is 2 ohm, this is 6 ohm, and this is 3 ohm. So again, we need to divide our calculation in a couple of parts. First, we find the equivalent resistance of this segment, and how is that? That is by finding the series equivalent resistance. So series equivalent is 1 plus 2, which is 3 ohm. So we write 3 ohm over here. 6 ohm remain as it is, and over here we have 3 ohm, which is as it is. Now this 3 and 6 are in parallel, so we got to find 1 over R equivalent, which is going to be, or let's say 1 over R, because this is not the equivalent resistance here. That's going to be 1 over 3 plus 1 over 6. So 1 over 3 plus 1 over 6 is over 6, and 2 plus 1. So that's going to be 1 over 2 ohm. So 1 over R is 1 over 2, which means that R is equal to 2 ohm. But that is not the final answer, because that is just the equivalent resistance of this part. So we're going to rewrite our circuit as these two, where this is 2 ohm and this is 3 ohm, this one. So between A and B, now we can easily get the value of R equivalent, because R equivalent is going to be the sum of these two resistors, because they are in series. So that's going to be 2 plus 3, which is nothing but 2 plus 3, which is nothing but 5 ohms. So this is the equivalent resistance between the points A and B. And let's take one last example in this, again a hybrid combination. So that's something like this. All right. So we have this as A and this as B. This is 3 ohm, this is 6 ohm, this is 6 ohm, this is 3 ohm, and this is 2 ohms. All right, so this can be divided in three parts. So the first part is where we calculate this equivalent, then we calculate this equivalent, and let's see how it goes from here. So if we calculate this equivalent, these two are in parallel, and these two are also in parallel. If we notice, their values are same. This is both are 3 and 6. So the equivalent resistance of 3 and 6 when they are in parallel is going to be 1 over R is 1 over 3 plus 1 over 6. So that's going to be over 6, 2 plus 1, which is 1 over 2. This is the value of 1 over R, which is 1 over 2. It means that R is 2. If R is 2, then this can be replaced by 2 ohms. This 2 ohm will remain as it is, and this can also be replaced by 2 ohms. So it converts into a simple structure in which three resistances are and resistors are in series. So their equivalent resistance is going to be same as the sum of the individual resistances, which is 6 ohms. So this is the answer for the equivalent resistance in this case. All right. Let's talk about the same kind of operation, but now we have the capacitor in the picture. So if we talk about capacitors, then capacitor is represented by, we already talked that it is represented by a bar and its unit is farad. Usually in the calculation, it is represented by microfarad because the farad is a pretty high value practically. So if we talk about the series combination of capacitors, then just like the resistors, the capacitors are connected in series like this. And if this is C1, this is C2, this is C3, this is C4, then their equivalent capacitance as opposite to the series combination of resistance, that's going to be 1 over C equivalent is the sum of the reciprocal of the individual capacitance. So this is how it looks like. And in the series, definitely their charge is going to remain same. So if this has a charge q, every capacitor which is in series will have a charge of q. While in the case of resistances, the current is going to be same. So in all of these resistances, the current is going to be I. While for the parallel case, if this is all connected to a battery of voltage V, then across each resistor, they will have a voltage difference of V volts across each of the resistance. So here the charge remains the same. While if we talk about the parallel connections, and the parallel connections looks exactly the same, even for the uh, capacitors as well. So as far as the looks are concerned, it also looks like a ladder. And just like resistances, the capacitor when connected in parallel will have a different charge. So it can have q1, q2, q3, q4, while the potential across each of the capacitor remains same, and that is equal to V, which is same as that of the external voltage in this case. So if their individual capacitances are C1, C2, C3, C4, then the equivalent capacitance is sum of the individual capacitance. That is how the parallel capacitors behaves. So it's exactly opposite to the behavior of the resistances and resistors in series and parallel. So let's talk about the examples. We have two capacitors which are connected between A and B. This is of 3 microfarad. This is of 6 microfarad. What is the equivalent capacitance? So 1 over C equivalent is going to be 1 over 3 plus 1 over 6. 1 over 3 plus 1 over 6 is 1 over 2. But mind it, this is not the answer, but this is the value of 1 over C equivalent. So taking reciprocal of both sides, C equivalent comes out as 2 microfarad. So this is the answer. Let's talk about another one. So we have a connection as these two capacitors are connected over here, while one capacitor is connected over here, and we have to find the equivalent capacitance between A and B. So again, although it is branched out, but it is in the same series connection. So if this is 3 microfarad, this is 6 microfarad, and this is 2 microfarad, again, we are going to say that all three are in the same series connection. So 1 over C equivalent is going to be 1 over 3 plus 1 over 6 plus 1 over 2. So it's going to be same as the common LCM is 6. This is going to be 2 plus 1 plus 3, and 6 over the 2 plus 1 plus 3 is 6, and 6 over 6 is just 1. So if 1 over C is 1, it means that C equivalent is also 1. The unit is microfarad. Let's talk about another question. We have these two capacitors which are connected in parallel, and we have to find the equivalent capacitance between A and B. So this is 3 microfarad, this is 6 microfarad. So what is the equivalent capacitance? Remember, we are not going to do 1 over C is equal to 1 over 3 plus 1 over 6. That's for series connection. But for parallel connection of capacitor, the equivalent capacitance is going to be just the addition of both. So that's going to be 9 microfarad. It can be a combination of series and parallel as well, just like resistors. So this is how the combination looks like. These two are in parallel, and it is in series with another one. So this is 1 microfarad, this is 2 microfarad, this is 6 microfarad. We have to find the equivalent capacitance between A and B. So first we find the equivalent capacitance of this, which is in parallel. So the equivalent capacitance is going to be the sum of the individual capacitances. So 2 plus 1 is 3. So that's 3 microfarad, and 6 microfarad is already outside. So now these are in series connection. So for series connection, 1 over C equivalent is going to be 1 over 3 plus 1 over 6. And 1 over 3 plus 1 over 6 is 1 over 2. So this means that 1 over C equivalent is 1 over 2, which means that C equivalent is 2 microfarad. Let's talk about another question. We can have a combination of the sort. We have 3 capacitances over here and another 3 capacitances over here, and we have to find the equivalent resistance between A and B. So this is going to be let's call it 3 microfarad, 6 microfarad and 2 microfarad, and we have the 6 microfarad here, 2 microfarad here, and 3 microfarad here. So you're going to divide this in three parts. First, we are going to find the equivalent resistance of the upper part, which is in series. So in series, that's going to be equal to 1 over C is equal to 1 over 3 plus 1 over 6 plus 1 over 2. So if we add this up, we are just going to get 6 over 6, which is nothing but 1. So C for the above one is 1. C for likewise the bottom side is also 1 because the values are same, 6, 2, and 3. It doesn't matter, the order doesn't matter. So again, the equivalent capacitance is 1. So we have now the simple circuit as 1 microfarad and 1 microfarad are connected in parallel. But if they are connected in parallel, the equivalent capacitance is going to be just the algebraic addition of both. So 1 plus 1 is going to be 2 microfarad, which is the equivalent resistance, equivalent capacitance, pardon. And the last one is another combination wherein we have these two capacitances in this form. In parallel, we have another one. We have one over here, then we have one over here, and then we have two capacitances over here, which is between A and B. So we have the values as 3 microfarad, 6 microfarad, 2 microfarad, 4 microfarad, let's call it 2 microfarad, 3 microfarad, and 6 microfarad. So we're going to do it in pieces. First, we are going to find the equivalent resistance of these two parts. So that's going to look like these are in series. So the equivalent resistance is going to be 1 over C is equal to 1 over 3 plus 1 over 6. So this is going to be 1 over 2. 1 over C is 1 over 2, which means that C is 2. So we are going to replace this by 2 microfarad. This is already 2 microfarad. Over here we have 4 microfarad. Over here we have 2 microfarad. This is also 2 microfarad because the values are same, 3 and 6. And now we are gonna simplify this further by taking these two into account. These two are in parallel, so their equivalent is gonna be just the algebraic addition. So 2 plus 2 is 4. Another 4 is as it is. And this is also 4. So these two now are in series. So for series connection, we know that the equivalent is going to be the sum of the reciprocals of both. So 1 over 4 plus 1 over 4 plus 1 over 4, which is 3 over 4. So the equivalent capacitance is going to be reciprocal of this, which is 4 over 3 microfarad, which is the final answer. So this was the certain examples on the series and the parallel combination of the capacitors and resistors. This is a part which is really helpful in solving complex circuits, and this is how we proceed in a sequential way for various combination of series and parallel resistors or capacitors. I hope you found this video helpful. Thank you so much.